Okay.
Good evening, and welcome all who are present here for this webinar on the growth of Himalayas and the Tibetan Plateau by Dr. Peter Molnar, a renowned geophysicist who pursued physics from Oberlin College in 1965 and earned a PhD in geology in 1970 from Columbia University. His initial works addressed aspects of plate tectonics, followed by a 2-year postdoctorate at Scripps Institute of Oceanography. He has also worked as an exchange scientist in the USSR, studying earthquake prediction, and later as an assistant professor at MIT, where he is specialized in deformation of continents and formation of mountain ranges on a large scale. In 2000, he studied the effects of large scale geodynamic processes on climate on geological time scales at the University of Colorado and became a fellow in the Cooperative Institute for Research in Environmental Sciences. Present here with us is also Dr. Ritesh Arya, co founder of Indian Geoparks and founder of Tethys Fossil Museum. He is a geologist known for finding water sources at multiple locations in the high altitude, cold, and mountainous desert of Ladakh, including Siachen Glacier, which made him a Guinness World Record holder. In 2014, he was appointed as the Director of Water and Geothermal Section at the International Sustainable Energy Organization in Geneva. He has a specialization in Himalayan geology and hydrology and is passionate about exploration of fossils, groundwater, geothermal, and understanding of tectonics and climate change, and is currently making a museum of evolution in Kasauli in Himachal Pradesh. For the last 30 years, he has been collecting fossils from Himachal Pradesh and Ladakh. I would now request Dr. Ritesh Arya to take over and commence the session.
Okay. Namaste. I welcome Dr. Peter Molnar, Professor Nigel Hughes, geologists, scientists from India and different parts of the world attending this webinar organized by members of Tethys Fossil Museum and Research Center supported by Indian Geoparks.in. Before starting today's deliberation, I will briefly tell about the Tethys Fossil Museum and Research Center, which is coming up at Dangyari, a small village in Kasauli Tehsil of Indian Himalaya. It is easily approachable from International Airport Chandigarh by road and railway, and a one-hour drive through different geological formations takes you a time frame of few million years to more than 60 million years. Geologically, museum is located on the debris concealing the Dakshai-Sabatu boundary, which signifies closure of Tethys Sea and evolution of terrestrial ecosystems. Museum is built from 20 million years rocks of Kasauli sandstone, beautifully chiseled to give museum an aesthetic look. Water which you drink in the museum is from a borewell drilled into 40 million years old white quartzite sandstone, which is marker pit extending from Pakistan to Burma in the east. Museum displays well-preserved fossils of stromatolites, ediacara, trilobites, mollusks, ammonites, etc. from Spiti Valley, fishes, whales, oysters, mollusks from Sabatu, logs of trees, leaves, flowers, roots, etc. from Kasauli and Dharamshala, and mammals from Shivaliks. All these signify gradual evolution of life on this planet and are part of the museum repository and will be ready reference for research scholars, geologists interested in research on Tethyan Himalayas. Tethys, as we all know, was once upon a time separating India from Tibet, Eurasia. As the India plate moved northward, the Tethys Sea squeezed, and when the two plates collided, the Tethyan sediments were uplifted, forming the mighty Himalayas. A lot of research has been done in timing the collision of the two plates, leading to evolution and birth of the Tethyan Himalayas. But still, there is no consensus, and there are Himalayan opportunities still waiting for researchers to come up with a convincing model to time the collision and explain the birth of Himalayas. Keeping this in mind, the organizing committee of Tethys Fossil Museum and Research Center decided to host a series of lectures by veteran geologists who dedicated their lives to understand this geomechanism. The first among these is Dr. Peter Molnar, who grew up seeing the plate tectonic theory proposed by Alfred Veterinary to reality, and at a very tender age decided to move to Southeast Asia and concentrate on studying how large-scale geodynamic processes cause deformation of Earth crust, including earthquakes and mountain and building of mountain ranges. He focused his research to know how shifting continents, emergence of islands, growth of mountains, etc., affect the climate on geological scale. So here I present Dr. Peter Molnar, who will be sharing his research and story about the growth of Himalayas and the Tibetan Plateau in today's webinar. Dr. Peter Molnar.
Okay, I'll start. Well,
Sure.
namaskar, and thank you, Dr. Ritesh. I'm happy to be here this evening to give you a talk, and I will share my screen. I will try to share my screen. There it is.
Yeah.
And so, as you said, I will be talking about the growth of the Himalaya and the Tibetan Plateau today. So let me just start right in. I'm going to show you an animation. This is an animation prepared by Tanya Atwater. Tanya Atwater is the mother of plate tectonics. And what's shown here is a cross-section through the Earth, the blue showing ocean. On the left is the Indian subcontinent. On the right, the rest of Asia, back 60 million years ago. Thin crust, the brown is crust, thin crust under oceanic regions, and crust being underthrust beneath southern Asia at 60 million years. You had a belt of volcanoes and thick crust in here. The red underneath is the mantle, with the dark red, the mantle lithosphere, the strong outer part of the Earth, the brighter red being the asthenosphere, the weaker part. So I'm going to run this animation. I'm just going to run this once. You can watch it and see what happens. India, as you see, continues to move north. It moves at an unabated rate into Asia. So let me do this again. Sorry, I want to advance the slide. And there we go. Nope. Okay, so I want to focus now on the collision that makes the Himalaya. Collision is at approximately 45 million years ago, so 60 were still before then. At that time, there was a narrow range like the present Andes along southern Asia, and India lay to the south. And the point here is that the Himalaya has been built by slices of Indian crust thrust atop the rest of the Indian subcontinent. So focus, when I run this, on this part of India, because that's where the Himalaya will grow. You underthrust, now a slice is brought up, and another slice, and you build the high peaks in here. The Himalaya consists of pieces of the old Indian subcontinent thrust atop one another. Now, we can know the position of India relative to Asia quite well. Here's a map. Here's the Tibetan Plateau in red. The Himalaya lie along the southern edge in here. And what are shown are positions with uncertainties of the Indian subcontinent, of that point and that point on the continent at different times in the past, 10, 20, 34, 40, so forth, million years ago. Here's India at the time of collision at about 45 million years ago. And here's India much further south in the southern hemisphere. There's the equator going across. And if we plot the distance from the present positions of these 2 points, one in the northwest corner and the other in the northeast corner, as a function of time. So here's distance, here's age going back. The collision takes place around 45 million years ago, and the rate that India converges slows abruptly at that time. The western part slows more abruptly than the eastern part. And that slowing continues, but India continues to move north at in the west, 34, in the east, 44 millimeters per year towards the rest of Asia. So India continues unabated. If we take apart the two sides of India and look back here at about 60 million years ago, this is a cross-section through India drawn at a 1-to-1 ratio. So we have water, blue, in the ocean of the Tethys Ocean, sediment on the edge of the continent. This is the Indian continent with crust that's approximately 35 kilometers thick, sedimentary rock on top, and then a continental margin giving way to oceanic crust. Further north, at 60 million years ago, one had a thick volcanic region of much granite intruding volcanoes at the top. The crust was thick, maybe 60 kilometers thick already before collision. And India is sliding underneath. Here is a deep sea trench, similar to what we have in the Western Pacific today. The blue is water again. The green is the thin oceanic crust, some of it scraped off in the forearc. And if we then look forward in time, I'm going to blow these up in a second, but if we're at about 45 million years ago, India is sliding underneath the southern edge of Asia. But then at some point, a new fault forms. This yellow line is meant to show a new fault breaking through the Indian crust. If we move forward in time to 20 million years ago, this corner between the top surface of India and this new fault slides underneath all the rock to the north and pushes that rock up into the air, pushes some of it back over on top of the southern Asian margin. And then another new fault forms, this pale blue line, that forms. And again, India slides underneath the boundary shown here. And because of this discontinuity in the slope here, all of this rock is forced upward as India slides underneath to tilt the rock on top backwards and bend the faults into this position. So if we just take a look back at 45 million years ago, this was the active subduction zone, and then collision occurs, a new fault forms. This is a new thrust fault. That new thrust fault ceases to be active at some point after slip has occurred. Another new fault forms, this one, and then moving forward again, the older fault becomes inactive and another new fault forms as you slide beneath India and beneath the Himalaya. India slides beneath the Himalaya. These are just cartoons. Don't take this too seriously, but this evolution of successive thrust faults is definitely a part of the Himalayan history. So if we look at a cross-section today, this is drawn by Avouak. We have out in front the Indian crust bent down, sediment in the Ganga basin. The Ganga flows through the basin in here, flows parallel to the Himalaya, of course. One has the main frontal thrust. This is the most active fault right at the front in here. The main boundary fault that once was active, the main central thrust, another earlier fault that's been warped, and then a bit of complication up in here, but the sedimentary rock on the top of India's former northern continental margin, the old oceanic rock between, and then the granite on the southern edge of Asia that was intruded before India collided. There's a bit of granite within the Himalaya also, but I won't be talking about that. I want to show you a couple of photos, a couple of photos from this area, and then another photo looking into this region. This is a photo taken out in front, the Gumbar thrust right out in front. Actually, this is no longer the active fault, but you can see conglomerate, cobbles, quite large cobbles here, a boundary coming along through here, and then this other sedimentary rock, this more fine-grained sedimentary rock. This has been thrust atop this coarser sedimentary rock in here at a fault like this, probably a fault a little bit north of this boundary. This is not quite the active one today. And here, one of the great Himalayan geologists of India, Vikram Thakur, has his finger on the thrust fault itself. You see the conglomerate underneath, you see a sharp boundary, and then you go into this finer grained material of the older sedimentary rock. that's been thrust atop it at that fault. I want to show you one photo from here showing you how this old thrust fault that once dipped at a gentle angle is now steep. So you have rock in here, highly sheared rock. This is the main central thrust zone, the major fault within the Himalaya, no longer active, but a major fault. Rock is highly sheared and dipping quite steeply in here. It dips steeply because this wedge with a ramp of steeper material underneath has been underthrusting beneath this area, and the rock above must rise to get out of the way of the path of this underthrusting material here. So one last brief discussion about earthquakes in the Himalaya. Earthquakes are inevitable. Shown first are a map showing where previous earthquakes occurred. In 1950, the great Assam earthquake out in this area, a smaller earthquake in Bhutan. In 1897, another great earthquake in the Shillong Plateau. 1934, the Bihar-Nepal earthquake. This did a lot of damage in Bihar to the south and in Nepal. This area, 1833, was an earthquake very similar to the earthquake that occurred a few years ago, the Gorkha earthquake, smaller than the 1834, but nevertheless a major earthquake. Not much is known about this in 1803, and then the 1905 Kangra earthquake. And we know that India slides beneath the Himalaya at about 20 millimeters per year. 20 millimeters per year. 20 millimeters per year, of course, means 2 meters in a century. And so if we look over the past half century, we should have accumulated about 1 meter of slip. Here's a scale on this axis of the potential slip. Accumulated 1 meter here. Bihar and Nepal, we're getting closer to 2 meters. It's not quite a century. The same with, we're up to 2 meters for the Kangra earthquake. But in the regions where we have not had an earthquake in the last 200 years, we should have 4 meters of potential slip, shown by these red lines. And if the last earthquake occurred further back, we would have greater potential slip, a potential slip of maybe 10 meters. So these are the potential slip. A 10-meter earthquake 10-meter slip will have a magnitude of 8.3 or so. The size of the earthquake depends on the amount of slip. So the earthquakes are inevitable. There's no stopping them. They will continue to occur. And the longer we wait, the bigger the earthquakes will be. But we have no control over this. So if I give you an interim summary of what I've said before I change topics, the Himalaya consists of thrust sheets stacked one atop another, slices of Indian crust. The convergence between India and southern Tibet and thrusting of India beneath the Himalaya continue unabated since collision. This process just continues. New thrust sheets of the top of India will be made in the future, but the convergence will not stop. And hence, major earthquakes are inevitable. So I'm going to change direction here at this point and switch to the Tibetan Plateau. And doing that, I want to show you this animation again, but this time we're going to, let's consider what happens since collision when India has penetrated steadily into Eurasia and shortening and thickening the Asian crust to build a wide, high Tibetan plateau. So focus on this area. This is crust starting off, I show it, or Tanya shows it here as uniform thickness. We know that's wrong now, but don't worry. This crust is going to thicken as India penetrates into Eurasia. So India penetrates, we build the Himalaya, but we thicken crust back in here by slip on thrust faults throughout India. And the crust beneath the Tibetan Plateau is roughly twice the thickness of the crust of India or the thickness of the crust further north in Asia. The crust has been shortened horizontally and thickened vertically. So crustal thickening by thrust faulting and folding in a state of area isostatic equilibrium, this is Archimedes' principle, this this isostatic equilibrium means if you have crust above sea level, you must have a crustal root below the bottom of the crust. That created high terrain in southern Eurasia, both before India collided with Tibet and early in the post-collision history. So I'm going to develop this in the next few slides. First, this is a textbook example of an unconformity. Here we have, this is a site just near Lhasa, 40 kilometers northwest of Lhasa. The Cretaceous Turkena formation is folded, very clearly folded. This rock is about 100 million years old. This is long before the collision. Lying on top is the Linzhizung formation, dated in this area at 69 million years ago. So this, and you can see the layers. This is lava flows. You can see layers and volcanic rock that may not have flowed, but it's all volcanic rock. Clearly, this rock was deposited on this folded rock after the rock was folded, but at this age, this is before the collision with India. So southern Tibet underwent crustal shortening. The rock in here to fold this rock means that the horizontal dimension must have shortened, and this must have occurred before collision. This is an important fact. Tibetan Plateau started to be built before India collided with Asia. And if we have a map of Tibet, there's a high range along the south, the Trans Himalaya, that existed before India arrived, but also a mountain range within the middle of Tibet, the Jangtang. This also seems to have been present before India collided. And I'm showing you here a cross section through this region between the Jangtang and the Trans Himalaya. So in the south, the Trans Himalaya would lie here. In the north, the Jangtang would be in this area. The yellow shows tertiary sedimentary rock, both before India collided and afterwards. The green is Cretaceous, so is this brown. So this is well before collision. The green is Cretaceous, right, and the brown is Cretaceous. And you have thrust faults where material has been thrust atop the tertiary rock. Here, Cretaceous atop Cretaceous, here above tertiary rock. And what these authors here have shown is present day length is about 65 kilometers. Restored length is 123. That means there's 58 kilometers of shortening, 48%. That's approximately doubling the thickness of the crust. So that if you shorten, if you bring this to shortened by a factor of 2, you double the thickness of crust. But the tertiary part is a large part. This is a minimum estimate, but it's by no means all of it. So much of the shortening occurred before the tertiary time. 25 is not 58. Another plot through here, a little less easy to understand. Here, this is showing at 50 to 30 million years, the Trans Himalaya with thick crust. Note this crustal thickness of 70. That's roughly twice normal thickness. The Himalaya have been built by 30 million years over here. The Jangtang lies in this area, and one has evidence of thrust faulting throughout the Jangtang in this period. But when one gets to the later period, 30 to 23 million years ago, there's just a little bit of crustal shortening. And the important point here is the shortening had ended by 20 million years ago. So collision near 45 million years ago, where you already had thick crust and shortened crust and high mountains probably, though we cannot know how high they were. And then by 20 million years ago, all of that stopped. And if we look on the north side of the Jangtang, up in here in the Hushil Basin, this basin, we see something similar. Here, the purple is rock of Triassic, Jurassic, and early Cretaceous age. The green going up into this brown is Cretaceous and early Tertiary age. So this is mostly pre-collision sedimentary rock. It's derived from the south on the left, where you had a high mountain range, the Zhangtang. So the Zhangtang shed sediment that went north and was deposited across this Kushiel basin. But then since that time, since 50 million years ago, when the sedimentation stopped, and hence since collision time, you've had thrust faulting and crustal shortening throughout this region. And they can date thrust faulting around the time of India's collision and since the collision up to 34 million years ago. But by 27 million years ago, this crustal shortening and crustal thickening had stopped. And they know this because they have flat-lying basalt, volcanic rock, lying on top of this folded sedimentary rock and dated at 27 million years ago. So there was deformation in here, but it stopped by 27 million years ago. And then since around 20 million years ago, there's evidence of widespread lake deposits. These green hatched areas and these blue regions, these are showing the locations of approximately 20 million year old lake sediment. So this must have been quite flat terrain going across here. This was not steep terrain because you wouldn't have had all these lakes if it were rugged mountains. And you have the same to the south of the Tonghua. The Tonghua is the present day high mountain range through here, relatively high. Again, lakes are widespread. Just to put you in context, this is Tibet, but at the top up in here is Golmud, just at the edge of the plateau, and Lhasa, the capital city of Tibet, down here is at this edge. So this region I've shown you is this box in the inset. A big wide area of Tibet with flat-lying lakes and flat-lying lake sediment, hardly deformed. Again, deformation had stopped. So give you another interim summary. Collision occurred at 45 million years ago, approximately. Some high terrain was built before collision. Crustal shortening continued for tens of millions of years, but crustal shortening within Tibet, not on its margins, stopped near 20 or 25 million years ago. So the whole of the deformation of Tibet to build a high plateau had stopped by this time. This is an important result. But it turns out it's a little more complicated. We had high terrain in the Zhangtang. We had high terrain in the Trans-Himalaya. The Himalaya itself was being built along the southern edge, but between the Zhangtang and the Trans-Himalaya were a system of basins. These were recognized as basins, but until recently, we didn't know that these were quite low basins. These are the Lumpala, Nyima, Gertsa basins in this area. And in recent years, Chinese scientists have gone in, and in the Lumpala basin, in this basin, they've found fossil plants dated at 47 million years. So these are just at the time of collision or maybe slightly before. And you see beautiful fossil leaves, rather wide leaves, long, slender leaves. You have seeds of various kinds. This is a flower. Again, leaves with teeth on their margins, long, slender leaves with drip tips. These are small leaves, but definitely there are leaves. And what they can do with the leaves, with those different shapes and sizes, is they can get a score that they will then use to infer a temperature. So each of these data points comes from some locality in a modern forest where they know the modern day mean annual temperature, and then they take the shapes and sizes of leaves and they calculate one number they call a vector score. So the data define a curve like this red line with a scatter. And then with the fossil leaves, they can go to this, get their vector score for the fossil leaves and read off a temperature with an uncertainty, clearly with an uncertainty in the temperature, of the fossil leaf assemblage when the leaves were alive. And if they take that 19 degrees C, they get approximately 1,500 meters pre-collision time in here. They can actually do better. I'm not going to go into the details of how they do this, but they can take these leaves and go directly to a paleo elevation. But the point here is that this basin, the Lumpala, and as well the Nima and Gyertsa basins, these were all only at about 1,500 meters, plus or minus 900, at the time of collision, when the Jangtang was high, we think, and the Trans-Himalaya was high. Again, 4,000 meters for the Trans-Himalaya, probably maybe the same for the Jangtang. So there was a belt of low basins in between. And they've gone further. Some of the same Chinese authors have found, again, in the Lumpala Basin, at 25 million years, evidence of palms. This is a palm frond. Here's a scale, 10 centimeters, a long palm leaf stem, and then the end of the palm frond. Again, more detail, blowing up a bit of the fossil itself, and then looking even more closely at the structure within the frond stem. Palms do not grow at high temperature. Palms cannot survive temperatures greater than, I think it's 5 or 6 degrees C. So they would argue that at 25 million years ago, the Lumpala Basin was below 2,000 meters. And putting this into a sequence of cross sections across Tibet from south to north, so south here, India would lie down here. Back before collision or early in collision, there was the Trans-Himalaya that was high, but the Lumpala Basin was low, then the Jangtang was high. And that was the case until 25 to 30 million years ago. Again, you have the evidence of the palms living in this area at 25 million years ago, quite low, 2,000 meters. But since that time, the area has risen, and the Himalaya has grown on the edge. So here's the Himalaya, Trans-Himalaya, the Lumpala Basin has risen, and the Jangtang here. And then we have the modern elevation up in here. No hint of a deep basin down in here. If they put that in a map kind of cross section with time, in Cretaceous time, before collision, the Tethys Ocean lay to the south. There was a shallow sea between the Trans-Himalaya, this is the Trans-Himalaya, and the Jangtang in here. At the time of collision or just before collision, this region probably was starting to dry out, but it was low. One still had the Trans-Himalaya and the Jangtang in this region, with thrusting beneath the thrusting of the Indian lithosphere starting to occur below southern Tibet, and then you build the Himalaya later next to the Trans-Himalaya and the Jangtang, and these basins then are still barely present, but they're not deep basins. The crust is thickened underneath. And this is my version of this 40 million years ago, a deep Lumpala basin. 25 million years ago, still a quite deep Lumpala basin between the Jangtang and the Trans-Himalaya. And then since 25, you've thickened the crust underneath this to bring it to the surface. And you've also thickened the crust under the Hushil Basin north of the Jangtang. Remember the Hushil Basin up in this region, north of the Jangtang, to build a cross section like what we have today. So if I were to summarize, crustal thickening by thrust faulting and folding in a state of area isostatic equilibrium created high terrain in southern Eurasia, both before India collided with Tibet and early in the post-collision history. So thrust faulting had occurred. Now, and I note, although high terrain was built before collision, there were still basins whose floors lay at only 2,000 meters and were present as recently as 25 million years ago. So there was an irregular structure. The Tibetan Plateau was not flat with just some high terrain. It had some very deep basins within it. Okay, now I changed direction again. A major change in the tectonic development of the Tibetan Plateau occurred at 15 to maybe 10 million years ago, maybe even a little earlier at 20 million years ago. As I mentioned, the Tibetan crust had stopped thickening. The shortening of the crust, horizontal shortening, had stopped, hence the thickening had stopped. And instead, the plateau began to spread apart, grow outward, and hence eastward, to become a wider plateau. Its crust thinned. Because of isostasy, its mean elevation began to decrease. And how do we know this? Well, we first know there's been a change simply from the earthquakes in Tibet. This is a map. The black line here is the 5,000 meter contour, as I recall, maybe 4,500 meter contour. Each of these symbols shows the location of an earthquake that we've studied, or I shouldn't say we, I'm not part of this, but that has been studied. And the Himalaya lie along the front of the bottom, the south edge of the Tibetan Plateau. And here, the red symbols show you thrust faulting. Thrust faulting where one piece of crust is pushed over the top of another, or one is pushed under beneath another. So the crust thickens in this region, as you have in the Himalaya around the edge. And you also have a hint of it along the northern edge as well. Thrust faulting around the edges. Within the high plateau, these blue symbols show normal faulting. Normal faulting occurs when you pull blocks of crust apart from one another. This block in what we call the hanging wall slides down relative to this block in the footwall, and the crust thins in this region. And these symbols, these blue symbols, are showing that the orientation of the faults is approximately north-south, so there's east-west extension. And you'll notice that the normal faulting is common where the elevations are high. This is elevation, 4,000, 5,000 meters. The normal faults are common in this region, except for this one exception where the process here is different. The Indian plate is bent down. And the thrust faulting occurs on the edges where the elevations are low. So the thrust faulting, you're still building high terrain around the edges, but within the plateau, normal faulting is occurring and crustal thinning is occurring. And normal faulting and crustal thinning cannot build a high plateau. This style of faulting in here is the opposite of building a high plateau. This is destroying the plateau. This is causing the plateau to become smaller or lower. So some change must have occurred. This is an inevitable consequence of the data shown in this plot. Well, when did this normal faulting start? So in the past 20 years, mostly in the past 20 years, many geologists have gone in and studied when did normal faulting begin? And numbers are like 13.5 million years ago, 13, 15, 10 to 8, 16 to 12, 14 to 11, and so forth, if you go around looking at all these dates. The onset of east-west extension of the plateau and crustal thinning occurred sometime between 15 and 10 million years ago, or started at close to 15 million years ago, but not the same time in all places. So this change in style of deformation occurred since approximately 15 million years ago. And we can look at this again with modern data using GPS. These arrows are showing you the velocities on a scale here, where this is 20 millimeters a year for these purple arrows. The white ones, it's 40. That's to make these not obliterate the whole map, but don't pay attention to the white ones. The purple ones, notice these are relative to India, so all of this is motion relative to India. In the western part of the Tibetan Plateau, there is a southwestward component of motion, whereas in the eastern part, there is a southeastward component of motion. So you have an eastward component here, a westward component there. Therefore, you have extension, east-west extension. That's the obvious consequence. And one can go farther. One can take these measurements and estimate strain rates, the rate at which the region is deforming, not just how it's moving relative to India, but how deformation occurs. And if you extrapolate present-day strain rates back to 15 million years ago or 10 million years ago, and assume area isostasy, so assume that when the crust becomes thinner, the mean elevation decreases by a fraction of that thin. That per meter drop in the mean elevation of Tibet. In other words, 15 million years ago, Tibet might have stood at 6,000 meters, not its present roughly 5,000 meters. It would have been an even higher plateau than it is now. So to summarize this, by 20 million years ago, Tibetan crust had stopped thickening. We know that already. Since 15 to 10, it began to spread apart. It grew outward to become a wider plateau. The crust thinned, and therefore the mean elevation began to decrease. These are inescapable conclusions if one takes the modern day data and the dates of the normal faulting, and one assumes that they apply to the entire region. I'm going to show this animation one more time, or actually two more times, but now I'm going to show it. But here I ask you to focus on the mantle lithosphere, the cold material, stronger material, the dark purple over here. As India collides, India pushes in, the crust thickens, but so does the mantle lithosphere, and eventually a blob of mantle lithosphere drops off beneath southern Tibet, and the mantle lithosphere under northern Tibet becomes thin. This material is unstable, so gravity tends to pull it down, and when it becomes thick enough, a blob drops off. I should insist this is speculative. This could be wrong. Many people don't believe what this animation shows, but this is my talk, so I'm telling you this, and you can decide whether you believe it or not. So the basic idea is simple. One has crust, which is of low density, overlying mantle lithosphere of higher density, which overlies a sthenosphere of slightly lower density than mantle lithosphere. And if you shorten horizontally, as shown by those arrows, and thicken the crust, because of area isostasy, you'll have high mountains, and you'll have a thick crustal root. But this higher density, thickened mantle lithosphere is a heavy load. This is denser than the material over there, so this pulls the surface down a little lower than it would be if that material were gone. Moreover, this is higher density than the neighboring material. It's unstable. It's like paint painted on a ceiling. It tends to drip off. So let's assume that happened, that this dripped off. So this pale blue is showing you mantle lithosphere that was removed from here. Well, the surface should go up a little bit because a load at the bottom has been removed. This is like unloading a ship. If you unload a ship, the rest of the ship rises. So the surface goes up a little bit, not 5 kilometers, probably 1 kilometer, maybe 2 kilometers, but not the whole of the Tibetan Plateau. Then we don't know how to describe, we call this deblobbing. But so the surface rises and available potential energy is given to the lithosphere. You increase, this has got potential energy which can do work. And what happens then is this is now high, it spreads apart. It spreads apart with normal faulting, with still thrust faulting on the margins. So the plateau, the high region in here, will become lower, but its margins will grow outward. It would become a wider plateau. Well, can we test this? What do we expect? Well, we'd expect lateral variations in density and seismic wave speeds because we have differences between where we removed mantle lithosphere and not. Enhanced volcanism because we've thinned the cold region and we've brought hot material close to the surface where it can melt. Crustal thinning beneath the high plateau, well, we've talked about that. Outward growth of the range, as this spreads apart, the margins will undergo crustal shortening. There'll be an increase in surface elevation at this point, and then followed by subsidence. As the crust thins, the surface will go down. And what can we do? And I will take you very quickly through just a little bit of evidence. I'm not showing you everything by any means. So this is a map. Here's the Himalaya lying down in here, the Tibetan Plateau across in this region, the Tarim Basin up here. These are PN speeds. This is PN speed in kilometers per second. PN is the P wave, the sound wave traveling at the top of the mantle. And nominally, when the speed, the P wave speed is low, we infer the region is hot. where the P wave speed is high, we infer that the region is cold. And you can see a hot region in northern Tibet and a cold region in southern Tibet in here, consistent with the picture that there should be lateral variations in seismic wave speeds. What about enhanced volcanism? Well, this is a map of Tibet, again, the Himalaya lying along the bottom, and across northern Tibet in here, quite young volcanic rock, basaltic, potassic volcanic rocks. This has got mostly basalt, or much of it is mantle derived, and quite young, ages of 3, 1 to 10, 16, 14 to 9, 13 to 7, 5, 1, so forth, 15 to 17 million years. Relatively young compared to the age of the plateau. And if you drive across northern Tibet, you see this. The hilltops are capped by basalt, as you see in here. This is all basalt on the top, where there's basalt under that too, under that snow. What about crustal thinning? Well, I've shown you this already. Definitely crustal thinning within Tibet. What about outward growth of the range? This map shows you the time when deformation began or accelerated around the plateau and since the collision at about 45 million years ago. The whole of the Tian Shan in here, there was a bit of terrain, high terrain here before 15 million years ago, but since then, 13 to 11, 11 to 10, 7, 11 million years, this has grown into a high mountain range. Lake Baikal started to open 10 to 7 million years ago. The edge of Tibet in here, 13 to 10, going around the edges in the same region, 15 to 10 million years ago, one sees the same numbers. The Shillong Plateau emerged sometime since 14 to 8 million years ago. So there seems little doubt that there's been outward growth of the plateau since 15 million years ago. How about an increase in surface elevation? This is a complicated plot, and what Ding and his colleagues are showing first is a map with some samples from the Himalaya and some samples from the Trans-Himalaya. I want to focus on this area, N for Nam Ling, and it's this site right in here. And this is a history of elevation change for the Lumpala Basin. You'll recognize that, the Nima Basin. Those are these basins up in here. And then since roughly 20 million years ago, the Nam Ling Basin rose somewhat, and it probably didn't start at sea level at this time for sure, but rose up at this time. So one could argue that we have an increase in surface elevation. And I should say I'm probably overselling this a little bit, but that's okay. What about a drop in elevation since that time? Well, this is the present elevation of the Nam Ling Basin. So there's been a 1,000-meter drop since 10 to 15 million years ago. And hence, we have both an increase in surface elevation and then followed by subsidence. I should emphasize again, I'm carefully picking data that support what I think. So maybe the arguments here are not as convincing as I'm saying. So if I were to summarize what's happened, India, the purple showing the crust of India, the blue, the mantle lithosphere, plunges under southern Tibet. You've scraped off parts of the crust to build the Himalaya. This is the old oceanic crust that used to lie between. That's the suture between India and southern Asia. The Trans-Himalaya has been high. The Lumpala Basin now high, and here the Jongtong high, the Hushil Basin. And in the mantle, one has mantle lithosphere that's been removed from northern Tibet. It's thin in this region, sinking under southern Tibet, as we've seen before. And so the northern Tibet, we have high temperature. This is the asthenosphere, and the reason this area is high is that it's got a hot upper mantle, thick crust plus hot upper mantle. And again, a bit more speculative, flow in the lower crust as convergence of material, both from the Himalayan side and from beneath the Jongtong, dragged crust in here, filled up the crust to make the crust under the Lumpala Basin thick enough to support a high basin. So I'm going to run this one last time just for you to watch, and you can focus on whatever interests you. This is meant to summarize everything. Tanya gave me this as a birthday present, and it honors my prejudices, but maybe not all of the facts. So you're free to doubt some of what is shown here. And if I summarize, I'll just read these quickly. The Himalaya has been built by underthrusting of India beneath southern Eurasia and the stacking of slices of India's upper crust. Crustal thickening and construction of the Tibetan Plateau began before the collision with India. This is important. This was not obvious until just a few years ago. Crustal thickening in Tibet stopped by 25 to 20 million years ago. Again, this is important. The deformation of the Tibetan Plateau by thickening and crustal shortening stopped. At 25 million years ago, Tibet contained high ranges with low basins between them. I showed you the evidence, the fossil palms and the fossil leaves for those basins. Then beginning near 15 plus or minus 5 million years ago, the plateau began to extend east-west, the crust began to thin, and elevations began to decrease. And then I would argue the most likely process leading to extension and subsidence is removal of mantle lithosphere. And with that, I am finished, and I'm happy to entertain questions. Thank you.
Dr. Ritesh Arya. Thank you so much, Dr. Peter. Such an invigorating presentation. We cannot even fathom the amount of research of years that must have gone behind this. It's really, really invigorating to watch and hear.
Thank you. Thank you. That's kind of you. I'm summarizing many other people's research, though.
Right. I think we should end. It was a pretty invigorating presentation, so I think we should end the recording with the presentation itself. What do you think, Dr. Ritesh?
You're muted.
Your mic is on mute. Still on mute.
So, Peter, thank you for taking us across the Himalayas and into the Tibetan Plateau and giving us a thought-provoking geological evidences, paleontological evidences, and the entire seismic evidences to support what you have been researching all these years. I must say that the most interesting part of your talk, which I felt was like, besides the animation which you showed made by Tanya, that the collision has been interesting right as we enter the geology department. This we just when we talk about Himalayas, this tectonic subsidence, India going below Tibetan plate, and the Himalayas evolving, and you have tried to explain it in a very simple way. But another aspect which I want to just show is that we have a lot of similarities in terms of fossils now, which we have found in Ladakh, about palm fossils which you showed, which were collected by the Tibetans or the Chinese scientists or geoscientists, and the plant fossils like the palm leaves. We have almost also got the similar size, or maybe bigger, in Ladakh now. We have got interesting findings of some foraminifera, some oysters, some bivalves from Ladakh, recent, and then comparing it with this Tibetan basin would be very interesting.
So where in Ladakh do you find these?
So my collection, we have found it in Nyoma, we have found it in Leh, we have found it in Kargil, we have found it in this Narula Basin. So all across, you can say the Suture zone, the south of Suture zone, we have found this fossils, and they are very well preserved, I must say. And no, so the slide which you showed, the first slide which you showed, one side was the Tibetan Plateau, the other one was the Indian Peninsula, and then we have this the Indus Malays or whatever we call the Tethyan Himalayas, and then we have this Ladakh Batholith, the the granite portion which you showed. Then the suturing which we consider is the Indus Sanko suture zone is like the suture between India and Tibetan plate is the suturing zone which we call it. But maybe now if the suture happens here and then it pushes further, and then this granite plays a very important role as far as I'm concerned, because now these fossils which we are finding in the southern part of the suture or Ladakh batholith or across this entire Indus Malays deposits. So these fossils and the fossils which you are finding in this the very interesting fossils and the very well preserved collection which you showed in your presentation, they were now, if the fossils deposited in Tibetan side were different, and the fossils which we get in the Ladakh or the south of Ladakh in this river are almost for the suture zone. They are different, and they have to be different, because we have such a big mountain ranges, the Trans Himalayan range separating the two, and then we have the Tibetan basins. But maybe once the palms, as you rightly said, cannot grow at these altitudes. Similarly, in Ladakh, also at 3,000 meters, we cannot expect palms to grow, and neither can we expect the oysters or the bivalves or the mollusks to grow, flourish. So, interesting thing would be to do this comparative studies of these two flora which we are getting now. But a lot of work has been done in the Chinese part, but we have just started finding, not me only, but a lot of scientists from Birbal Sani also found a lot of fossils, palms. But I have got a very, very big collection, maybe 1 meter or more than that, the fossils which we have found. Now, interesting thing, again, I will come back to your presentation. If timing of collision is believed to be 40-45 million years, and the fossils which we are getting in Ladakh and also in the Tibetan basin, they are about 20-25 million years. Same fossils. I'm also expecting the age to be Miocene, low Miocene, equivalent to you can say the Kasauli formation or the Dharamshala formation or the Murray formation in Pakistan. So if we have this fossils here, and if we have the same fossils of palm layer and 20-25 million years there and 20-25 million years here, at that point of time, based on the fossil evidences, that collision is not possible, because at that time they were just very much near the elevations were very much, as you rightly said, was 1015, maybe 900 minus, so maybe around to 400-500 meters above the mean sea level, which you showed in your presentation. And then the collision timing has to be very, very lesser than 20-25 million years. That is my submission. Based on your research, which I found it very interesting, because I had no idea what was happening in the Tibetan Plateau, and what you showed me with this presentation really interests me a lot now. And with the findings which I had, I firmly believe that the collision was not happening at that time, because the fossils of the on the two sides, maybe on the Trans-Himalayan side in the Tibetan Plateau and the southern side of the Sanko suture in the Ladakh Malays, they showed me that the elevations were maybe around again 600-500 million meters over the mean sea level, and since they are from the low Miocene sediments, so maybe around 20 25 million years, or maybe 18 million years to 20 to 23 million years, these were not elevated to the present levels. So the collision timing has to be something different. I like to just ask you, what is your opinion about these? Yeah.
Well, I don't think I have a plot that can help us here, but there's no question that when you get to Ladakh and all the way to Pakistan, it's not quite. The record is different from what one has farther east. So, as you probably know, the Indus suture and the Shayak suture merge in eastern Ladakh.
Mhm.
There's a controversy that I think is becoming resolved, but it's not. I don't follow it closely, and it's not my work. And many people think that the Indus suture in that part of the region was not between India and Eurasia, but between India and an island arc that lay offshore. So this would mean that the batholith just above Leh, and I don't remember the terminology, so I don't know if that's the Ladakh batholith or
Yeah, Ladakh Batholith they call it. Yes, you're
yeah.
right.
So the Ladakh batholith, if this is correct, and if I remember correctly, that would have been beneath an island arc. And hence the collision could have been earlier, could have been 60 million years ago or some other time, but it would have lain further south because at that time India was further south. And then there was a basin between that arc where the Ladakh batholith was and the rest of Eurasia farther north. So this basin is like the Sea of Japan, or it's like the basin behind the Tongan Arc between Tonga and Fiji. This is, or it could be like the Black Sea and the Mediterranean, an isolated basin. That basin, then that collision between India and the Ladakh batholith with Eurasia occurred more recently, and presumably occurred closer to 45 million years ago. The 45 million year number that I'm using is not based on any contact between India and Eurasia that you map geologically. It's not mapped by the disappearance of marine sediment. It's based on when India slows down. So India moves north very rapidly and then it abruptly slows down. And the logical reason for it to slow down is that subducting continental crust is difficult. It's buoyant. It's like trying to subduct an air mattress. It's too buoyant. It doesn't want to sink. So that date is when India changed its speed. It's not necessarily when contact was first made by two peninsulas. So regarding your fossils, then the question would be, where are they? And are they south of the Ladakh Basin? Well, then they're on India, and it's a different situation. If they're on the north side in the Shayak suture, then the question would be, are they part of, on which side of the Shayak suture? Are they on the Ladakh batholith side or the Eurasian batholith side? And if they're on the Eurasian side, then indeed they could be the same age fossils as those in the Lumpala Basin. What I didn't tell you in this talk, because there's not enough time, but and now let me show you, actually, that's worth showing you. Oh, sorry. I wanted to go to. So looking at this map, I showed you results from the Lumpala Basin. There's less overwhelming evidence from the Nema Basin, and it would take me a bit of time to find it. The Giertsa Basin has a very interesting result. I skipped completely the discussion of oxygen isotopes because they've been used, oxygen isotopes in pedogenic carbonates, they've been used as paleoaltimeters. In general, they're not reliable, I think, once you get north of the Trans-Himalaya. But they found in the Giertsa Basin evidence that this region was possibly at sea level and possibly with marine sediment. They found foraminifera that look marine. And so if that were the case, this would have been open to the ocean. Well, where would the ocean be? The ocean has to be to the west. That's the only place. And then if you go into the Kailash region, Kailash is right in here. The history of the Kailash region allows for this to have been low. So the Trans-Himalaya we draw with this picture, but it's possible that back 40 million years ago, these basins extended past where Kailash is and further out into open ocean out in here. And 45 million years ago, all of this rock in here, this is the Srinagar. What do I want? What you would know the name? This is the basin.
Srinagar Basin, yeah.
Srinagar Basin. So Ladakh is further west. But at 45 million years ago, the Ladakh batholith could have lain way down here somewhere. And the southern edge of Asia probably didn't lie that far south, but you would have opened into an ocean that was out in here. So it's possible that your fossils were not at a very different latitude, a little bit further north of these in the Giertsa Basin. And they have moved north, of course, because the movement relative to the Pamir. But they would have lain out here as a continuation, and there would have been a gap. And so the Trans-Himalaya might have just stopped near Ladakh, near the Kailash region, and what lay further northwest, well, we don't know, but it might have been different. So your fossils, if you have fossil palms and you have an age, they might fit very nicely with what's been found over in here. What I would do, I would encourage you, the person I'm in contact with, so Su et al. Su is a young Chinese, but the person I'm looking for. So Spicer is a British scientist. Su, that's the same.
Yeah, he was with me. You know, we did. You can say he was my guide in one of my chapters in my PhD thesis.
Okay, well, he's the expert. He's the person who. I mean, I've never met Su. Su's a young man, and he does very good work, no question about it. So I don't want to take away any credit to Su, but Spicer is generous, and so he doesn't this is a review paper. This is published in a Chinese journal. You never would have seen this journal, but Spicer wrote for them. But Spicer is in Su's et al. You know, it's Su et al. And Spicer is, I don't know, third or fourth in the list. And the same is true in this paper. Spicer is, there are 20 authors.
This
Spicer,
is quite.
I would contact Spicer if I were you. I would write to him. If you want, I can. I'm in contact with Spicer quite regularly.
Okay, that's very good.
And so, shall I write to the two of you? Just send you and him a note.
Oh, why not? Why not?
Okay.
If that can be done, maybe. And then another thing on this, I'll just briefly touch that point, that all these fossils which we are getting in Ladakh and Kargil fossils, and the fossils which I find in Kasauli. Now, Kasauli is, you are aware about Kasauli? No?
Yeah, I don't know where Kasauli is. It's
It
except
is
it's where your
it is it
museum.
is it is near Shimla, you can say, between
Okay.
Chandigarh and
Yeah, yeah.
Shimla. Between Chandigarh
Okay.
and Shimla.
Yep.
So all the fossils which we are getting from Kasauli, we are getting in Kargil also.
Huh.
And the Kasauli fossils now, with Birbal Sahni Institute of Paleobotany, Lucknow, we have found that all these fossils which we are getting there, they are having affinities with Indonesia and Malaysian fossils. Now, this is very interesting. This Spicer has already seen all these specimens when I was doing my PhD. So he visited my site in Kasauli. So, but at that time we had identified only 2 species. Now we have identified about 7 to 8 species which have very close affinities with the fossils which we find in Andaman Nicobar, which we find in today in Indonesia and Malaysia. So I want to bring the Solly formation, that is Shimla, Dharamshala, and maybe Murray also. Further, maybe 4 to 11 degrees north of equator at the time of deposition of those sediments. So, because otherwise you cannot explain these occurrence of these fossils of Garcinia gluta, Caesium, maybe 6, 7 species which we have identified, which we have affinity with Andaman Nicobar and Malaysian, Indo-Malaysian regions. So the entire concept of deposition of these and Ladakh sediments shifts back to uh, 4 to 11 degrees north of equator at the time of deposition, that is about 20 million years back. So my
Oh my
assumption
gosh.
is 20
20
million.
million years ago at that latitude.
At that latitude, yeah.
Whoa, whoa. That's
So
hard to believe.
because the fossils are like fossils, they won't lie, and the plant fossils which we are getting, they show these 6, 7 species. They were part of my PhD also in the and I published a small paper in 1994 Geological Survey of India Lucknow seminar. I presented that these have to be, and then my limiting factor in not because Ladakh batholith forms a very good barrier, and all of a sudden this entire Indus malaise, it just goes and thrusts itself against Ladakh batholith.
Yep.
So Ladakh batholith is a batholith, and then we can't expect any migrations before or after happening there. So now the question is, when we're talking about this timing of collision, so if my Kasauli formation and Savatu and Dakshai, maybe about the sequence which you're talking about is about when you talk about 40 million years, that is about end of Savatu Sea and continental environment. So this is already happening near the equator only, and India India is just colliding those sequence near the equator, and then this entire mass is thrusted, and then this moves the entire along with the solid Akshai, maybe Murray sediments and Chitravata formation in Pakistan. And then this entire sequence is thrusted due to the Indian movement, But the deposition of these takes place near the equator because of the huge palms which you're getting, all the fossils, foraminifera, oysters, all these similarities which we are finding. And so, and if we can draw, and then these were, as you said rightly, in the Tibetan Plateau, there may be an ocean then at that time, and then there was some island arcs and all, and then this. What do you feel about this? Sorry, I'm again asking another very vague question that is from you, and that is this Ladakh batholith. Was it in situ or was it also transported?
Well, that's I mean, I don't know. I know what I read, and I believe I've come to accept what's been written recently, that the Ladakh batholith, as I said, I think I'm right, that it was part of an island arc.
Yeah.
So it could have lain in the southern hemisphere 40 million years ago.
Okay.
Or very near the equator. But so could 40 million years ago, the Trans Himalaya was at only 10 degrees north.
Yeah.
So it was way farther south. It's been closed.
So
But the
then,
Ladakh batholith was isolated from Eurasia, and a hint of that you see in Oman. Oman is covered with not covered with, but it's got a nice belt of ophiolites that are 93 million years old, thrust on top of Arabia back at that time. That's probably part of this same island arc
exactly.
that
Yes, I agree
included
with that.
with the Ladakh bath. So then how much space was there between the Ladakh batholith and southern Eurasia, the region further north, the region where the Shayak suture is now? Well, 20 degrees, there's no problem bringing it close to the equator. How much ocean floor lay between? Well, quite possibly 2,000 kilometers.
Yep.
I think that's an open. So then, but where is all of the rock that was part of that 2,000 kilometers? Well, it's gone. It's subducted. It's in the mantle. It's gone. And then you still have sedimentary rock deposited on parts of that accumulated on the edges of the Ladakh batholith and on the edges of the north side of the Shayak suture. That's all now juxtaposed very close today, but the two sides could have been far apart long ago. How much, I don't know, and finding what's missing, again, I don't know. But I would think that if you've got fossil assemblages that are well preserved, it's possible to do paleomagnetism to determine the latitudes.
Okay.
This will have been rotated around a vertical axis, so there's lots you cannot learn, but you can get a paleolatitude and learn whether this was in the southern hemisphere or at the equator, or was where near its present day latitude of 32 or 3 degrees north. That's possible. I would strongly urge paleomagnetism. I'm trying to remember. Again, I would contact Spicer. Spicer works with Indian paleobotanists. One of them's name is Khan, Khan, but I don't. That's a common name, of course, and I don't know him. I think they're in the Sani Institute, but I'm not even sure of that. And then he has another Indian colleague. They've worked farther east, over in Assam and in that region. But Spicer works closely with Indian scientists. He has a good relationship with Indian scientists. At least it seems to me that he does. And he has a good relationship.
Yes, you're right.
So he gave a lecture at the Sani Institute back. There was a conference there a few months ago. From Britain. Everything is, of course, remote. Anyway, I think Spicer can help you most. I can send you. I have a paper that's going to be published next week in Himalayan Geology that covers much of this. I got the proofs just last week. I can send you that. It's got a very, very long reference list, most of which won't help you at all. It's geophysics and it's other stuff. And I don't, but it does cover. It gives the references to all of this paleontology that I talked about today. That's all covered in there. So I'll send you that. But it sounds like you have something very interesting, and I think Spicer.
Yes, that is why I was so fascinated to make this Tethys Fossil Museum, based on this collection, so that anybody can come, have a ready reference for all the fossils which we have collected and the models which we are going to propose, the new model what we are going to propose for the timing of the collision, and the timing, because we have got so many fossils of shivalics, and it is very difficult to explain such big elephants, such big tortoise, such big lions, everything, giraffes in the foothills of Chandigarh, or the foothills of Himalayas. So they have to be deposited somewhere near the equator, because That is their habitat. If you are talking about giraffes, modern day habitats, the big elephants, the propensity of
Well, giraffes can have evolved. There are giraffes in Pakistan that I don't know how old they are, but giraffe fossils, and they don't have such long necks as I understand. They're giraffeids. They're not really giraffes.
but here the museums yeah, I think so. So I'm so happy that you are so open to the discussion, and then it was really very interesting to have you with us, and to start the series of talk which we intend to continue with a lot of geologists who are working in the Himalayas, and especially, and to have you on board and start the talks with you, series of talks. It is really a blessing for us. And
Well,
we look, yeah.
it's kind of you to say that. I do urge you to get Spicer to. Spicer can talk. Spicer gives good talks, so I encourage you to consider him.
Spicer also, and if you can, because I was seeing the Crawford Award which you got, and the series of lectures given by various geoscientists from all over the world.
Yeah.
In that seminar which was awarded by Swedish.
Yeah.
I saw all the presentation at that time, like 2014, I think it was there, and then I was quite impressed by by the work, and some of the students whom you taught are now leading professors in the MIT and all institutes.
Well, I was lucky to work with some very bright students, but I also was lucky. I worked with Valdia, and that.
Valdia, okay.
we never published together, but we spent a lot of time together. So this paper is dedicated. It's a volume dedicated to him.
Oh, really? Okay, good. And VC Thakur is now in Himachal Pradesh. We did a project on seismology together. 4 seismic stations in main boundary fault, main central thrust, and Shivaliks we installed. I was in a drilling company then, and then we did some borewells and then installed that seismographs. Though it didn't work out well, but it was a good beginning to just make a beginning in understanding the seismology and the earthquake studies in Himalayas. Across, we wanted to make stuff. So, Peter, thank you very much. And
well, thank you, and good luck.
Like this, we can we'll just open up a chat, and whenever you are free, we can just have some more insights in a very, very lighter way. How you started in working in Himalayas and how you went in Tibet. We will be more interested because these things which will be fascinating to the children, because you're a legend in Himalayan geology, and we want to just show how you got interested in Himalayas, and maybe next time we come up, it will be more of about you, your story, your journey in Himalayas, and some interesting incidents which you remember. Just try to, that will be beyond this presentation if you can, but it will be a lighter side of Peter Molnar, where he'll be talking to children. So I will try to arrange that. If not, we'll just try to take you back to your childhood and your graduation days, and how you were fascinated with geology, rocks, and how earthquakes came, and then how you started plate tectonics, and then you shifted to continents, and the entire journey we would like to hear about you. That would be more interesting for us, in next talk, if you are interested, sir.
Well, I'm not particularly interested in talking about myself. So
no, it's not about you. It's about your journey and the rocks, and your understanding how gradually you build up the entire story. It's about giving an inspiration to the youngs. That is what would be very interesting to the young geologists. How they start their journey and become Peter Molnar, or maybe develop big concepts, or try to understand Mother Earth or the Himalayas in general. So maybe in next talk we'll like to be see this aspect of yours. If you're interested, sir, I will be very grateful to you, sir. Anytime.
Well, it has to wait. So
no problem. Yeah. That's not you're not in a hurry to do it, but yes, we love to do it.
Okay.
Because these talks, everyone has seen all these talks everywhere, but how did you do it? How did you figure out that yes, the crustal thickening, and then the shifting from Himalayas to the Tibetan Plateau, and how I can visualize, because at that time when I started my journey in Ladakh, it was in 1996. It was not easy to work at that time also, but Tibet was again further, and it was very remote, and how you did it at that time when nothing was there, and for dedication. So all these points we would like to cover in that talk. And we wait for your answer, and when you are prepared, you just let us know, and we'll be happy to have you again.
Okay, we can do that. In the
Yeah, thank you very
meantime,
much.
I'll send a note to Spicer and see if I can get you hooked up with him.
Yeah, then we can have Spicer talking about this same thing, and we can just have a talk with him also.
Yep. Okay.
Okay. Thank you, Peter. Thank you very much. Namaste.
Okay.
Thank you, Ashim.
Namaskar.
Bye bye.
Bye bye.
Bye bye. Bye bye.